Hello everybody, in this video I will solve some problems about the Lagrange multipliers. I will start the first problem. It is related with the rectangular box, and if you remember, this problem is at the beginning of the theoretical part of the Lagrange multipliers in the first video, and in that video we solved this problem using substitution and using the idea of critical points. But in this time I will solve it using Lagrange multipliers, and you can see the difference of these two methods. Okay. So first of all, I will define x, y, and z be the length, width, and the height of the box, respectively. Then the function to be optimized here is the volume, because we are looking for the maximum. Find the maximum volume, right? This is in the statement of the problem. We are looking for the maximum volume, so this is the function to be optimized. In other words, it is the function to be maximized in this problem, in this case. Okay, so it is the x times y times z. And also we have a constraint function here. Why? Because we have just 12 square meter cardboard here. Okay, we can only use that amount of cardboard to make this rectangular box. So because of that, the constraint function here is that the area of that box should be equal to 12 square meter, and the area is xy plus 2xz plus 2yz equals 12. Okay, so as you can see, we have a constraint function in the form g of xy equals k. Okay, so this is a level curve of that function actually. Okay, so now using the Lagrange multiplier method, we look for the values of x, y, z, and lambda such that we should show, in other words, let me write first of all these. The gradient volume should be equal to lambda times gradient g, the constraint function. Okay, the method of Lagrange multipliers says that you should show this equation and this equation at the same time for x, y, z, and lambda. Okay, and we are looking for the solutions of those equations. So let's look at that part. First of all, the gradient of f means the first partial derivatives of f with respect to x, y, and z in the components respectively. So I have this, and here I have g sub x, g sub y, and g sub z, right? So let's try to find the first partial derivative of f with respect to x. Here y and z constant, and the derivative of x is 1, so I have yz in the first component, and derivative of y will be xz, and derivative of v with respect to z is xy, equals to lambda times derivative of that function for this time, this function here with respect to x is, here I have y, and here I have 2z, and there is no x, so this is constant. Derivative of this part is 0, and with respect to y, from here I have x plus, there is no y, so derivative of this term is 0, and but from here I have 2z, and the derivative of g with respect to z is, this will be constant, and so derivative is 0. I have 2x plus 2y. So we have actually 4 different equations here. Okay. Why? Because, let me write this first time like that, xz, xy. If I distribute this lambda here, then I will have lambda times y 2z, lambda times x plus 2z, and lambda times 2x plus 2y. We have 2 different vectors, and they are equal, so it means the components of these vectors are equal. So we have following 5 equations to solve here. First of all, yz equals lambda times y plus 2z here xz, second component, equals this second component, lambda times x plus 2z. And third component, xy, equals lambda times 2x plus 2y. And also we have one more equation here, 2xz plus 2yz plus xy equals 12. So we have 4 different equations to solve, and we are looking for x, y, and z and lambda which satisfy these 4 equations at the same time. Okay. There are no general rules for solving systems of equations, okay, like that. But in the present example, in this example, if we multiply the first equation with x, okay, and second equation with y, and the third equation with z, we will obtain x, y, z on the left-hand side of these equations, right? So because these sides are equal, the left and right-hand sides of these equations should equal also. So I will multiply first equation with x, okay, x, y, z equals lambda times 2xz plus xy. Here x, y, z equals, we just multiply this equation with y, okay? So I have lambda times xy plus 2yz. And this equation with z, x, y, z equals lambda times 2xz plus 2yz. Okay, and this is same here, okay? So I have 2xz plus 2yz plus xy equals 12. So let's call this equation 5, and this 6, and this 7, and this still 4, because we didn't make any change here. So first of all, we should observe that here lambda cannot be equal to 0. Why? Because if lambda is 0, here 0, 0, 0, then we will have here, if you look at here, yz equals 0, xz equals 0, and yz equals 0. Okay, so and if I substitute 0, 0, 0 in the third equation, then I will obtain 0 plus 0 plus 0 equals 12. So this is a contradiction. Because of that, lambda cannot be equal to 0 here. Okay, let me write it. Lambda cannot be equal to 0, since if lambda is equal to 0, I will have xy equals xz equals yz equals 0 from 1, 2, and 3. Okay, so it means x is 0, y is 0, and z is 0 here, okay? And then x is 0, y is 0, z is 0. Then we will have, actually not x is 0, y is 0, z is 0, at least one of them. If you look at here, y or z should be equal to 0. If y is equal to 0, z no need to be equal to 0. But here, because z is not 0, x should be equal to 0. So I have x and y 0 at the same time, and 0, 0 equal to 0. But if you substitute x is 0 and y is 0 here, you will obtain 0 plus 0 plus 0, which is 12. Okay. Or if y is not 0, z should be equal to 0 for this time. If z is 0, then we have 0, 0 here. But here, y is not 0. So x should be equal to 0. Must be, actually. So again, because x is 0 here, we have 0. Z is 0. X is 0. Again, 0 is equal to 12. We will obtain. So I can say that. So at 2 of at least 2 of x, y, and z are 0, okay? It means in 4 we have 0 equals 12, and this is not true. So lambda cannot be equal to 0. Okay, if lambda is not 0, for this time we can analyze 5 and 6 and 7 separately. Okay, so if we analyze, if we equate 5 and 6 here, let's write this one also. Since lambda is not 0, from 5 and 6 we have lambda equals 2xz plus xy equals lambda xy plus 2yz. Because lambda is not 0, I can cancel them. So I have 2xz plus xy equals xy plus 2yz. Okay, so here I can cancel common terms here. 2xz. Is there any problem? No, there is no problem. Xy's will be cancelled. Sorry, this should be cancelled. Yz still here. So I have 2xz equals 2yz, which means xz equals yz. Okay, we have this first of all. But z is not 0. Why? Because if z is 0, volume will be 0. So it is not the maximum value of the volume. And also if z is 0, we won't have a box. Okay. Then, since z cannot be equal to 0, because if z is equal to 0, volume will be 0 and we won't have a box here, we can cancel z. So I have x equals y. Okay, from 5 and 6 we have this. On the other hand, from 6 and 7 I have the following result. Lambda equals xy plus 2yz. Lambda times xy plus 2yz equals lambda times 2xz plus 2yz. So from here we have lambda will be cancelled because it is not 0. Xy plus 2yz equals 2xz plus 2yz. I can cancel 2yz, so we have xy equals 2xz. And again here, since x cannot be 0, because if x is 0, again we will obtain 0 for the value of the volume, and we won't have a box here because one side of this box is 0. Then I can cancel x's, so y is 2z. Okay, so at the end we have the following equalities. X is equal to y, y is equal to 2z. So how can we find x, y, and z? We didn't use this fourth equation. Okay, if we substitute x equals y equals 2z here, then we will obtain values. Put x equals y equals 2z in 4, we get x equals 2z here. 4 is this. Okay, I just substitute x equals 2z and y equals 2z here, and x equals 2z, y equals 2z. So I have 2 times 2z times z plus 2 times 2z times z plus 2z times 2z, which means I have 4z squared, 4z squared, 4z squared, so 12. Z squared equals 12. So z squared is 1. Because z is a length, it is positive, z is 1. If z is 1, x is 2. Why? Because x is 2z, y is 2z, and y is 2 also. So the maximum value occur, hence maximum volume is V, x is 2, y is 2, and z is 1, which is 4. Okay, so this is the way of solving this problem using Lagrange multipliers methods. Okay, let's move on to next problem. And here we want to find the extreme values of the function f of xy equals x squared plus 2y squared. And on the circle, x squared plus y squared is 1. Okay. Again, first of all, here we should write the function to be optimized. Function to be optimized. And again, in this case, we just want to maximize it. Maximized is that function, because we want to find the extreme values of that function. F of xy equals x squared plus 2y squared. Okay, and the constraint function is g of xy, and it equals to x squared plus y squared equals 1. This is the circle. So for this time we have two variables functions of two variables. Okay, so now I will use Lagrange multipliers, and it means I need to solve the following equations. Gradient f equals lambda times gradient g, and g of xy equals x squared plus y squared equals 1. Okay, let's start with this part. Gradient f is f sub x, f sub y equals lambda times g sub x, g sub y, and it means derivative of this function with respect to x is 2x, and with respect to y is 4y, equals lambda times derivative of this function, this g of xy, with respect to x is 2x and 2y. So if you distribute lambda here, you will have 2x lambda and 2y lambda here. Okay, so the equations are 2x equals 2x lambda, and 4y equals 2y lambda, and g of xy here, x squared plus y squared equals 1. For this time we have three different equations to solve. Okay, and let's start with the analysis of the first part, first equation in this problem. First equation. If you look at the first equation, I have 2x equals 2x lambda. So I can take this to this side. So I will have 2x in the common parentheses 1 minus lambda equals 0. It means x is 0 or lambda is 1. Okay. So I have two different possibilities. I will start with x is 0 and analyze the second equation. Okay. So second equation, second and third equation at the same time, actually, further analysis, and third equations here. If x equals 0, I can find y using the third equation. Okay, y 3, 0 squared plus y squared is 1, so it means y squared is 1, so I have 1 is minus 1 or y is 1. Okay, so if y is minus 1, I can obtain lambda using the second equation, but there is no need to find lambda because we are looking for only the points. So points are here, points, x is 0, y is minus 1, x is 0, y is 1. Okay, if lambda equals 1, we have two cases. X can be 0, lambda can be 1. If x is 0, using second and third equation, I obtain the points. When lambda is equal to 0, lambda equals to 1, then I can use these equations to obtain points. And for this time, because lambda is in the second equation by 2, 4y equals 2y we have. Okay, which means 2y equals 0, so y equals 0. If y is 0 for this time by 3, because we should find x also, if y is 0, then I will use 3 to find x's. I have x squared plus 0 squared is 1, so x squared is 1, so x is, let me write here, x is minus 1 or x is 1. Okay. The points are, for this time, points are x is minus 1 but y is 0, and x is 1 and y is 0. Okay, so we have four different possibilities here. Okay, we have 4 points. Points. 4 points. Let me write them. Minus 1, 0, 1, 0, 0, minus 1, and 0, 1. So to obtain the maximum value, I need to evaluate f at these points. Evaluate f at these points. So f of 0, 1 is, what is f? F is here, f of xy is given in the problem as x squared plus 2y squared. So f of 0, 1 will be 2. F of 0 minus 1 will be 2 again, okay? And f of 1, 0 will be 1. And f of minus 1, 0 will be again 1. Okay. So as you can see, we have 2 and 1 as results, and we are looking for the maximum value. So therefore, maximum value of f, maximum value of f on the circle x squared plus y squared equals 1 is occurred at these points, which is 2. F of 0 minus plus 2 equals, minus plus 1 equals 2. Okay, and the minimum value is 1, but in the problem we asked for the extreme value, so I should write the minimum value also. Minimum value of f on this circle is f of minus plus 1, 0, which is 1. Okay, so here I should write maximized and minimized, because we are looking for the extreme values, not maximum or not minimum, in both of them. Okay, let's continue with the next problem. And in this problem here, now we want to obtain the extreme values of the same function, but for this time not on the circle but on the disk, on this disk. Okay, again, the function to be optimized is f of xy equals x squared plus 2y squared, and the constraint for this time, constraint is g of xy equals x squared plus y squared equals 1. Okay, we solved this part. We solved this part in the example 2. Okay, so this is the boundary case. Boundary case. But because here we are we have a disk, for this time we should analyze the inside of this region also, and we know that the inner part of inside part of the region can be analyzed using the critical points. Okay, to analyze inside of the disk, we will find critical points. So it means I need f sub x, which is 2x, and f sub y, which is 4y, equals 0, 0. From here I have x is 0, from here I have y is 0. So 0, 0 is the only critical point of this function. But we should check whether or not it is inside the given region. So to do this, I will substitute it in the given equation for the region. 0 squared plus 0 squared, which is 0, is less than or equal to 1. So 0, 0 is inside the region, given region. Okay, now for this time we should compare more than 1 point, because in this part, in the former question, we have from this part, we have 4 points, f of minus or plus 1, 0, and we obtain this as, what was the value of this function? It is 1, okay, and f of 0 minus or plus 1 is 2, and from here I have a critical point inside the region. We have 1 point, which is 0, 0, and f of 0, 0 is 0 here. Okay, so as you can see, result is changed. Maximum is same, but minimum is changed here. So the maximum value of f on the in the region x squared plus y squared is less than or equal to 1 is f of 0 minus or plus 1 is 2, and the minimum value of f in the region in this disk, given disk, is f of 0, 0, which is 0, sorry. Okay, so I just want to compare these two results here. In the former question, we are on the boundary of the disk. We have just a circle, and we analyze this circle using Lagrange multipliers, and we have obtained 4 different points, and we calculate our function at these points and obtain 2 and 1 as a result. So the maximum value is 2, minimum value is 1. But if you have a disk, a region, not only boundary, for this time you don't have inequality here only, right? The equality part represent the boundary part, and you can analyze the boundary case using Lagrange multipliers. But you should analyze the inside of the region using the critical points idea also. Okay, because of that, here from the boundary we have 4 different points, and at these points the function takes the values 1 and 2. But after the analysis of the critical point here, we have obtained that 0, 0 is the only critical point, and it is in the inside of this region. So we should analyze this point also, and if we calculate our function at this point, we obtained 0 as a result. So if you compare 0, 1 and 2, you will conclude that 2 is the maximum value here and 0 is the minimum value. So on the boundary of this region, 1 is the minimum value, 2 is the maximum value, but on the whole region, 0 is minimum, but the 2 is the maximum value. Okay. And this is the end of this part. See you on next part.